Hi and welcome. I'm Zong Yang. I'm your tutor for today. And welcome to our live tutoring session. We will be solving the entire paper for IGCSE Physics, subject code 0625, Winter 2025, Paper 4, Set 2. For today's session, we will be going through the entire question paper and explaining how to solve each question in detail. I hope that everyone here finds this useful. Please take note that we will answer 15 appropriate questions from the live comment section regarding the paper we are going through and other IGCSE physics questions on a first-come, first-served basis. The questions will be vetted by our physics tutor, Narayan, so please do submit your queries if you have any. Without further ado, let's begin with today's session. Alright, so give me a second. You go here. And I think we can begin here. All right, so I guess everybody can see the paper right now. This is paper 4, set 2 from October, November 2025. Let's begin. Before we begin, right, can we have a quick shout out to the comment section? The chat, can you see me? If you can, please say something on the chat. All right, so let's hang on for a short moment. Okay, and I guess we can begin. All right. Okay, so let's begin today's session right now. All right, so firstly, let's begin our paper with the usual basic physics things about vectors and scalars. So this is a very simple question. The first part of question A1, the first question A1 does give a very simple question you need to solve. Basically, we need to know what's the difference between a scalar quantity and a vector quantity. Simply put, a scalar quantity has a magnitude. However, a vector quantity have both a magnitude and direction. So we just need to write this down in our question paper, right? So firstly put, a scalar quantity only has magnitude. Oops, my bad. Okay. While a vector quantity has both magnitude and direction. Pretty easy, just like that, 1 mark right down. That's done. So let's move on with our second part of A1A. All right. So in the list below, we have to draw a line under each of the quantities that is a scalar quantity. So as we have mentioned before, scalar quantity only has a magnitude, while a vector quantity has both magnitude and direction. So let's go through these one by one. Acceleration has both a magnitude and a direction. So this is a vector. This should not be the answer. Next, mass over here, we only have a scalar. Basically, you cannot measure how many kilograms in one direction, right? So mass is one of these quantities. So we should draw a line. I bet it is a little bit crooked. I have to bring a ruler this time round. Right, let's move on. Next, momentum. Momentum does have a magnitude, which is momentum is basically force multiplied by the displacement traveled. And of course, because of that, momentum has a direction. So momentum is a vector quantity, and this should not be part of it. Next, electric field strength also have a quantity and also a direction, because you can, if you remember electric fields, right, they do have a direction with all these arrows and stuff. So because of that, electric field strength is also a vector. Now this last two, energy is in joules, and you measure energy you don't really measure what direction the energy is. So of course, because of that, energy should also be a scalar quantity, right? Right. Sorry. Thank you, Narayan sir. So just to give you guys a quick update, momentum is a product of mass and velocity. So that is good. That's a good thing from Narayan sir's side. Thank you. Yeah. Right. Next thing. Last but not least, temperature. Right. Temperature is in kelvins, and the thing is you cannot really measure temperature, and temperature does not you cannot temperature doesn't really have a distance, have a direction. I'm so sorry about that. So because of that, temperature is also a scalar quantity. Oh dear, my bad. All right, so temperature should also be a scalar quantity. There we go. Yeah. Yes, as Narayan sir has mentioned, momentum, for momentum, right, is the product of mass times the displacement, plus times velocity. Thank you so much. And the direction of the momentum goes along the direction of the velocity. So basically that's that. And because of that, let me just remove this. Okay. All right, and just like that, 2 marks settled. Right. Next, let's move on to part B. Yeah. Okay. Okay, so now part B. Let's go through this question. So a tennis player throws a tennis ball into the air. The mass of the tennis ball is 5.8 times 10 to the power of minus 2 kilograms. The tennis ball leaves the tennis player's hand and reaches a maximum height of 5 meters above the point of release. So essentially, this is the tennis player. He throws the ball. Is it he or she? He throws the ball upwards. They throw the ball upwards, right? And it reaches a maximum height of 5 meters. Okay, so we need to show that the initial velocity of the tennis ball is 9.9 meters per second upwards. Basically, around here, you must show that the velocity is 9.9 meters upwards. All right. So how do we solve this question? Simply put, we need to know that the kinetic energy of the tennis ball over here, when it is launched, right, it converts completely into gravitational potential energy at the top of its path. So all the kinetic energy here is equals to the maximum the maximum gravitational potential energy on the top of the path. So let's write that down, right? So kinetic energy of ball, which is initial, right, is equal to the gravitational potential energy of the ball final. Right, so long story short, over here, kinetic energy is maximum. When it reaches the top here, kinetic energy is 0 because it converts completely into GPE. Same thing over here, GPE over here is 0, but when it reaches the top, the GPT is the max because all the energy of the kinetic energy is converted into GPE, right? So first we need to write half mv squared. This is Ke, right? Kinetic energy is half mv squared is equals to mgh, which is gravitational potential energy at final. And by just writing this, you get 1 mark already. Okay, so this is 1 mark. Next thing we do is we cancel out the mass on both sides. So we just cancel here, cancel there, right? Now we get half v squared equals to gh. Okay, now v squared equals to 2gh. V is equals to square root 2gh. Now let's write down some things. G is equals to 9.8 meter per second squared, right? So let's write that down. 9.81, and h is 5 meters. Okay. Now you do the calculations, right? You will get this, right? And then you will get 9.89, how many nines are there? There's probably a lot of nines here, right? Meters per second, right? And now you have to convert everything here into two significant figures. So you get 9.9 meters per second squared. And of course, you must write two significant figures. Okay? Yeah. 1 second. Like that. And that's our answer. All right. So we have shown that the ball moves 9.9 meters per second upwards. Okay? All good? Now, let's move on with part 2. All right. So, part 2, we have to calculate the momentum of the tennis ball as it leaves the player's hand. So just now, we have already stated that momentum, which is P, is equals to the mass of the tennis ball multiplied by the velocity of the ball, right? So the ball, the tennis ball already has been given the mass, which is over here, 5.8 times 10 to the power minus 2, right? So let's write that down. Right, multiplied by 9.9 meters per second, which is given right here, right? So we will get, after doing the calculations on the calculator, we'll get 0.5742, so on and so forth, because there's a lot of the, actually there isn't, my bad, right? And then we should turn this into two significant figures, which is 0.57, right, kilogram, which is from the mass here, and we have the speed, the velocity here, which is meter per second. So this will be our answer. All right. This is also in two significant figures. Right, let's write that down. All right. So do take note, right? Once you write down this equation, P equals to M times V, you get 1 mark here. And then when you get the correct answer, you get another mark here. That gives you 2 marks. All right. So just to give you guys a heads up here, although the question does not specifically ask for direction, it is always good practice to assign a direction to any vector quantity. So for example, over here, the velocity here is moving upwards, right? So for this question, since right the velocity is directed upwards, as we have said over here, the momentum here should have an upwards direction. So we should write here upwards. Okay, all good? Right. Okay, so let's just be sure that we keep as a good habit to make sure that there's always a direction to be written in every, any vector quantity. So as we have stated before, this is a vector quantity, or momentum is a vector quantity. Good. All right. Now let's just take a look at the let's see, look through the comments and see if there's any comments or any questions. Oh, be better. Yeah. Oh, yeah. I see. All right. That should do. Be better now. Okay. Okay. Now, all right. Thank you everybody for the good comments. Thanks also for giving the recommendations. Yeah, my face is blocking everything, so oops, my bad. But now you should be able to see my wonderful drawings and silly little graphics over here. So, right, without further ado, let's move on with the questions. The next question. Let's move on to question number 2. All right. All right. Question number 2. Okay. If you guys can't see anything, please let me know, yeah? Okay? I will try my best to adjust the gremlins of the question. Give me a second. Let me just put this down a little bit more so I think we can all see this nicely. Fantastic. Okay, let's move on. All right, so for question 2, part A, right, a truck moves at a constant acceleration. The speed of the truck increases from 13 to 22 meters per second. All right, so for this, we do see a truck, right? It moves at a speed of 13 meters per second and it increases speed to 22 meters per second. The time increase of this speed is 4.5 seconds and the mass of the truck is 3,700 kilograms. So we first need to calculate the resultant force acting on the truck. That seems like a lot of information you need to process. All right. So let's break this whole question down. So first things first, do take note that we have constant acceleration, which means force is constant, right? Because constant acceleration is constant. So from this whole question, we can see that, right? The question gives you a few key points. Number one, the speed of the truck increases from 13 to 22 meters per second. And the time taken for this speed is 4.5 seconds. So first things first, let's find the acceleration of the truck. My goodness, this is horrible. Okay, so acceleration of the truck is equals to change in speed divided by change in time. Okay, pardon my handwriting, this is horrible. Let's just continue that. All right, so it be equals to 22 minus 13, right, which is 22 minus 13, and then divided by 4.5 seconds. And with that, we get 9 divided by 4.5, which you get 2 meters per second squared. This is our acceleration, okay? Now, writing this, change the speed over time, right, will get you 1 mark. To take note, okay? Now, moving on, right? Now we need to equate, force using the acceleration and the mass. As you do know, from Newton's second law of motion, force is equals to mass times acceleration. We're given the mass of the truck, which is 3,700 kilograms, right? Multiplied by the acceleration, which is 2.0 meters per second squared, right? By doing that, you'll get, doing the calculations, 3 times 2 equals 6, 7 times 2, 4, so you get 7,400 newtons. Okay, so we have our resultant force as 7,400 newtons. Do remember to keep the to write down the units, right? This is very important. Not writing this down won't get you a mark. Okay, 1 mark here, do remember, and 1 mark here. All right, fantastic. Everybody clear so far? Okay. Right. So we now have found the force acting on the truck. Now we need to state the two forces that are acting on the truck in the opposite direction of this forward force over here. All right. So immediately you do know that as the truck moves forward, let me just bring my silly little drawing again. All right. As the truck moves forward, this 7,400 newtons, right? There should be two forces dragging it backwards. Okay. So the first force, as you can see, a truck goes through air, so it should have air resistance. That's the first force. All right. The second is when the wheels touch the ground, right? We have something called friction. And so these are the two forces that are acting on the opposite force, the opposite of this forward driving force. Okay, so let's write it down. It's pretty simple, isn't it? So the two resistive forces are air resistance or we can also call it drag, right? And friction. Between the tires and the road, right? So writing air resistance and friction will give you 1 mark each, giving you 2 marks in total. Okay, all clear? Fantastic. All right. So this is a very simple question. We're now done with part A. Now let's move on to part B. All right. Now, as you see here, figure 2.1, which is here, right? You see a car traveling around a circular racing track. This is the topic of circular motion. As you can see, the car moves here, the track looks like this, right? And B part 1 says that the car moves at a constant speed. So you must draw an arrow to show the direction of the force acting on the car. So in a circular motion, for an object undergoing circular motion, assuming that it is moving at constant speed, there will be only one direction of force, right? And that one direction of force is here. It will be here, and it acts towards the center of the circle, right? This is the force. We call this centripetal force. Okay, yeah. So this force is centripetal force. All right. All clear, yeah? Okay. Now let's move on to part 2, to B part 2. Now, the question states that a different car travels around the track and then slides off the track at part P. So essentially, the car did a whoopsie and it flies off at P. So we need to state two possible reasons for the car to slide off the track. Why does a car slide off the track instead of going around in a circle, right? So for a car to actually slide off to actually move away from this circular motion, right? It could be a few things. Number one, the centripetal force is not enough, right? So there most likely, right, it could be the car is traveling too quickly. That's why it flies off the track. It also can be the case that the car is too heavy and the centripetal force is not enough to keep the car in the track. And there's also a case that the car tires do not have enough friction with the track. Maybe the car tires are bowed or something. And because of that, there's not enough centripetal force, and the car just slides off the track. So do take note that, right, this question is asking for two reasons. So you can write two possible reasons. So over here, give me a second. All right, so let's write the first possible reason. First possible reason is that the car might be traveling too quickly, and the tires okay my bad, does um does the centripetal force is insufficient to keep the car on the track. Okay, and next thing we can say that is the car tires do not have enough friction, okay, the track. Thus, the car don't have enough centripetal. So sorry, we have a guest. Centripetal. Oops. Force. Okay. To keep it in the track. Right. So to take note, right, since this question is only asking for two possible reasons, please don't write more than two reasons. Okay? Yeah, so 2 marks, two reasons. Okay? So without is everybody okay with this question so far? Oh, good, yeah? Yes, we have a very cute guest. She is currently trying to be silly. Okay. All right, Lily, I know you are trying to teach people physics, but please get off. Thank you very much. All right. Okay, let's move on. Let's continue with the lesson. All right, now we are done with question 2. Let's move on to question 3. Question 3, look, we are talking about solar panels now. This is about energy. All right, so let's move on. Okay. So question 3 shows, right, the figure here shows black solar panels installed on the roof of a house, and it has a large rechargeable battery. So the solar panels produce electricity and gives a maximum power output of 3.5 kilowatts. And the efficiency of the solar panels is 16%. So here's some keywords to take note. The solar panels have a maximum power output of 3.5 kilowatts, and the efficiency of the solar panel is 16%. All right. So this will come in later when we are doing more, calculations. But first, 3 part A. Oops, my bad. All right. So 3 part A wants you to state and explain one advantage of using black solar panels. Right. So why are solar panels black or usually in a very dark color? So as we do know, right, black has this very interesting properties where black is a good absorber of radiation, right? Which means it actually absorbs all the colors of radiation. If we were to do, right, let's say solar panels in red, it will only absorb red and it will reflect away all the other colors. So that's the reason why it's black. So that's really one reason. All right. And having more energy absorbed means more energy generated by the solar panels. And that makes the solar panel much more efficient, right? So let's write that down. Actually, you know what? Let me just type it down. It's a bit easier and it's nicer to write. Right, so let's just type it down. So that is a good, my goodness. That is a good absorber of radiation. So it will absorb more radiation. Okay, this meant more energy. Right, this meant more energy generated and makes the solar panels more efficient. Okay, there we go. Fantastic. Maybe I can make the text a little bit bigger. Yeah. Is this a good text size for you guys? Maybe too big. That's good. All right. So yeah. So we need to, here as you can see, we need to state and explain. So state is 1 mark and explain is the second mark. So we get 2 marks out of it. All right. Now let's move on to part B, which is the quantitative one, the quantitative part of the explanation of the answers. All right. So next, we need to calculate the power received by the solar panels from the sun. Okay. So as we do know, the solar panels stated in this question has a maximum power output, which this is the output by the way. Okay. And of 3.5 kilowatts, and the efficiency of the solar panels is 16%. So which means this 3.5 kilowatts is the 16% efficiency. This is the power generated by the solar panels. All right. So we do know that, let's write this down first. Efficiency, right, is equals to the power output divided by the power input and multiplied by 100%. Okay, right. So as you see here, efficiency here is 16%. Okay, 16% efficiency, okay, equals to power output of 3.5 kilowatts divided by power input divided by 100%. Okay, now let's do the maths, right? Power input to go here. So let's do it this way. Equals to, okay, 3.5, right, divided by 16 over 100. Okay, and that gets you this. And now let's round this up to 2 significant figures as per usual. Remember, this is a very good habit. Please do that. And please write 2 as F as per usual. Okay, so for this question, you see there are 3 marks. The first mark is when you write you bring in the correct values into the equation like this. So this is 1 mark. Okay. Then next, there's another mark awarded here for the correct way of doing the mathematics, and the last mark is given is the correct answer. Right. So the correct answer is 22 kilowatts. All good, yeah? Fantastic. Okay, now that is done, let's move on to part C. Wow, more qualitative answers. Very nice. So more writing. Right, so as you see here, the solar panels produce more direct current and household appliances uses alternating current. So two things need to take note here. Direct current, DC, alternating current, AC. So state the difference between AC and DC. Okay, I know AC/DC is a band, but we are not doing that here. We are just going to talk what's the difference between alternating current and direct current. Actually the answer is already in the name, so let's write it down. So a direct current, a DC, right? The current only moves in one direction. So let's write that down. Oh my goodness, what happened to my handwriting today? So sorry. Let me just try and write this properly. A DC, okay. Okay, produce current only, okay, it only moves. Okay, move only in one direction, right? Wow. And AC reverses its direction. Theoretically. All right, so there we go. Yes. Also, I think a better way to show it, thank you Naran sir, by the way, for sending in this recommendation. As you can see in a DC, this is the time, right? This is time and this is the current, right? A DC, it's constant, right? But in an AC, it goes like this. It's a sine graph. It could be a sine graph, it could be anything, but it alternates like this. So it goes from positive to negative. Okay? This is DC, this is AC, right? Very good. Now, let's move on a little bit more. Okay, so part D. Suggest one advantage of storing storing energy in a large rechargeable battery. All right. So let's move to this, right? So there are many advantages of storing this. Basically, number one, if you have any spare energy that's generated by the solar panels, you can store it in the battery and to use it at night. So when there is no energy source, for example, no sun, you can use it. You can use electricity that's stored by the battery. Okay, yeah. So this is actually the only advantage for now. So let me just write it down. This is the answer that we will have. So suggest one advantage. So storing the energy, right, in a battery, right, allows okay, allows electricity to be used at night. Okay, where there's no sun. To generate electricity. Okay, so that's one. The other option is maybe, when there's cloudy or it's raining or the sun is blocked by clouds or any, weather conditions. This answer works as well. Okay, right. Now, another quantitative question, right? So let's calculate the charge that flows into the battery when there's a current of 4 amperes for 2 hours. Oh, okay. So we are now to calculate the charge, okay? And the current is 4 amperes and it flows for 2 hours. as you do know, charge is equals to, oh my goodness, is equals to the current multiplied by time. But do take note, right, the time must be in seconds as the SI unit. So first, let's convert 2 hours into seconds. So let's do this. Time taken is 2 hours, right? To be equals to 2 times 60 minutes equals to 2 times 60 times 60 seconds. Now that gives you 7,200 seconds. Okay, this is the first one. This gives you 1 mark. Okay. Now we bring this back down. Charge is equals to current multiplied by time. Okay, that would be equals to current, which is 4 amperes, multiplied by 7,200 seconds. And that gives you 28,800 coulombs. This is the SI unit for charge, okay? Coulombs. C is equal to coulombs. Right? Okay, now as per usual, don't stop there. We have to convert this into two significant figures as per usual. So 29000. Remember to write this thing. All right. And then this C, which is the unit, and then let's write 2SF like that. Okay. All right. So charge is equals to 29000 coulombs. Okay, I just got a request from the chat, right? That we want to repeat question 3B. So let's finish let's wrap up question 3 and then I will explain question 3B again. Okay, everybody? Good. All right. All right, fantastic. Okay, let's move on. Let's go to, since question 3 is done, let's go back to B. Okay, to 3 part B. Let's go through this part of the question right now. So first things for this question, right? You want to calculate the power received by solar panels from the sun. So as we are given from the question itself, the output of the solar panels is 3.5 kilowatts, right? Okay, and the efficiency of the solar panels is 16%. What does this mean? This means, right, the output of the solar panels is 16%. The output of 3.5 kilowatts is 16%. So the input energy, which is energy from the sun onto the solar panels, is much greater than this 3.5 kilowatts. And we have to find the input energy, which is right down here, as you can see. So basically, we use this equation, efficiency equals to power output divided by power input multiplied by 100%. So the efficiency is 16%, so we plug it right here. And the power output is 3.5 kilowatts, which also equals to 3,500 watts, right? So let me just rewrite this a little bit right here. So the power output is also 3,500 watts. Okay, that makes it easier. And then you divide it by the power input multiplied by 100. So you do the mathematics, power input, you multiply on both sides, and you divide 16% over the other side. So basically you divide 16% on both sides and you multiply power input on two sides. So power input goes in here, 16% goes back underneath here. Okay, so that's how you get power input is equals to power output divided by 16 over 100, which is 16%. So that gets you, actually no, this should be kilowatts, my bad. I'm so sorry. That's silly. 3.5 kilowatts. right here as well. Right. So the power input is equals to 3.5 kilowatts divided by 16%, which gets you 21.875. And you do the conversion, you basically round this thing up because it's 21.8. Is 0.8 here, so you round up, so you get 22 kilowatts in two significant figures. And this is how you get answer of 22 kilowatts. The significance. Okay, you don't understand the significant figures. Okay, so for significant figures, right, it's pretty simple. So for example, let's have numbers 1, 2, hang on a minute, that's not right. All right, so for significant figures, right, two significant figures means the first two numbers from the left, basically this number and this number, we want these two numbers only. The rest we want to eliminate. But how we eliminate this is pretty straightforward. Any number that is below 5, basically 0, 1, 2, 3, 4, we round downwards. So 0, 1, 2, 3, 4, we round downwards, and with 5, 6, 7, 8, 9, we round upwards. So we take the next number of the significant figure, next to the significant figure to the right. This is the number we are looking at. So 8 is basically greater than 5, so we need to round upwards. And that's why 21 becomes 22. Yes. So this is how we round up or round down. And it doesn't have to be, decimal, it doesn't have to be decimal place. You can also round up numbers like, let's say, 3, 7, 6, 4, 2. You want to round it into 3 significant figures. So we want to take the 3 most important numbers, which is 3, 7, and 6, right? We want to eliminate these two numbers. But the thing is, right, these two numbers, we want to take a look at number 4 here. This is the number you want to check. Since 4 is lower than 5, you can write it like this now. 3, 7, 6, 0, 0. We convert these numbers into zeros. And then since 4 is lower than 5, the number becomes 0. If let's say this is a 5 instead, for example, if this is a 5, we will actually turn this into 3, 7, 7. Okay? So far so clear? Chat, is everyone clear with significant figures? All right. So another question over here is, which color is the second best absorber? Apparently, there is no answer to that because we only know in the IGCSE syllabus, right? White is the best reflector, and black is the best absorber. So essentially, any other colors like blue, red, green, all these colors, right? It reflects all other color frequencies. For example, red, it will only absorb red wavelengths. For example, if this is red, only red wavelengths will go through. It will absorb. As for the rest of the wavelengths, you get reflected. Like let's say this is blue, this is green. All other wavelengths will be reflected, but only red will be absorbed. So there's not really such a thing called, second best absorber, but maybe second best can be something that is a bit, darker in color. That's pretty much it. Yeah. Okay, all good? Let's go. Let's continue. All right, so for the person who asked about the significant figures, is everything okay? Right, if that's good, let's move on with our questions. Now, just give me a second. I need a drink of water. Okay. Right, let's begin question 4. Okay, so question 4 is quite straightforward as well. Question 4 shows gas trapped in the cylinder by a piston. Okay, and this volume of gas is 240 centimeter cube. in here. And the piston is pushed to the left. So it is pushed this way, and held in its new position. Okay? So part 1, A part 1. The pressure of the gas increased from 1 times 10 to the power of 5 to 1.4 to 10 to the power of 5 pascals. This is the unit for pressure. Okay? And the temperature remain constant. Okay? So now we need to calculate the volume of the gas when the piston is in the new position. Alright, so this question pretty straightforward. We do know that pressure times volume equals to constant. Okay, in this situation, so we can write pressure 1, volume 1 is times volume 1 equals to pressure 2 times volume 2. Oops, let's write it a little bit neater. 2. Okay, so let's put this down. So this is pressure 1, this is pressure 2. Temperature remains constant. Okay, so the volume of the gas, which is the initial volume, is this. Okay, so we need to find V2. This is the subject we need to find. So let's rearrange this afterwards. So let's do this. So pressure 1 times volume 1. So pressure 1, 1.0 times 10 to the power of 5 multiplied by 240 centimeter cube is equals to pressure 2, 1.4 times 10 to the power of 5 times volume 2, which is in centimeter cube as well. Okay, cm cube. So let's do a little bit of manipulation. So let's keep V2 over here, bring this over there. Then we get V2 is equals to 1.0 times 10 to the power of 5 times 240 divided by 1.4 times 10 to the power of 5. Okay, now we do the calculations, do the mathematics, and we get 171.428. Okay, and as per usual, let's convert this into two significant figures, which is 170 centimeter cube, which is in two significant figures. All right. So to take note, if you write this, PV equals to constant, or P1 V1 equals to P2 V2, this gives you 1 mark. Okay, and when you try to solve the equation like this, that gives you 1 mark as well. And getting the correct answer gives you 1 final mark. That gives you the total 3 marks of this question. So 170 centimeter cube. Okay, all good. Everybody good with this so far? Yeah. Yeah, I'm getting very good, feelings from everybody. This is really an easy paper. Paper 4.2 is one of the easiest papers so far. Yeah. Okay, everyone, all good? Yes. All right. Fantastic. All right. So let's move on. All right. So A part 2. The area of the piston in contact with the gas is 1.9 times 10 to the power of minus 3 meters squared. So this area, as a piston, you can see, right? The out, and this is the thing you use to push, right? Yeah. So it's talking about this area over here. Okay. The plunger over here. Yeah. So this is the area they want to calculate. Okay. So we want to calculate the force exerted on the piston by the gas when the piston is held in its new position. All right. So for this, it feels like quite a bit of things is happening, but not to worry. We already been given quite a lot of the things. For example, we need to know that, well, the piston is held in its new position. So in this new position, we already been given the pressure of the gas is increased to 1.4. So pressure is equals to 1.4 times 10 to the power of 5 pascals, right? Right? That is our pressure that's exerted already. So we also do know that pressure, is equals to force over area, right? We also been given the area that is in contact with the pistons, which is 1.9 times 10 to the power of minus 3 meters squared. Okay, so we now need to find the force. So let's do a bit of calculations. Let's bring A over. So F is equals to pressure times area. Okay, pressure is 1.4 times 10 to the power of 5 multiplied by area, which is 1.9 times 10 to the power of minus 3. Do note that it's already in meters squared, so we don't really have to move anything, don't have to change anything. So let's do the calculations again. Now we get 2.66 times 10 to the power of 2 newtons. Okay, and doing the rounding down again, rounding up again this time around because it's 6. 6 is greater than 5, so you get 2.7 times 10 to the power of 2 newtons. Or we can write it as 270. Not newtons. I'm so sorry, it's not newtons. It's newtons? It's newtons. My goodness. 270 newtons. Also okay. Yep. So now that is done, let's write 270 newtons down here. Okay. All right. So do take note, right, that when we do calculations, we try to, do everything using try to do as much as possible using the SI units. For example, this is meter squared, so it makes the calculation a lot more easier. Okay. Okay, all good. Great. Chat is looking very active now. Someone is saying it's still looking very easy. That's fantastic. All right, let's move on. So, okay, everybody clear with this question so far? Yeah, so all good, yeah? Let me just write a few more things down. This is pascals. This is in meters squared. All right, fantastic. Let's move on. Okay, now let's move on to part 3. All right. So it is stated that the distance moved by the piston is 0.036 meters, and the average force exerted by the piston is, as it moves, is 220 newtons. So this, let's not use it anymore. Let's go to here. All right. So the distance moved, as you can see, the piston, as we seen just now, right? Okay, the piston. This is the original, and then this is the new one. It moves a total distance of 0.036 meters. Okay, it moves this way. So we are to calculate the mechanical work done. All right. So as you do know, work done is equals to force times the displacement or distance traveled. Okay. So this is equals to 220. Oops, my handwriting. This is a disaster. My handwriting is very bad today. All right. So we have the work done, the force exerted as 220 newtons here, multiplied by distance, which is 0.036 meters, all right? And that would give you 7.92 joules, right? Joules, which is the unit for energy. And now let's do the conversion. Let's do the significant figure thingy. 7.9 joules. Okay, two significant figures. There we go. 7.9. All right, joules. Okay, pretty simple, yeah. As long as you write the equation, work done is equals to force times distance, you get 1 mark. You get the correct answer, you get a second mark. Right. All good. Right. Finally, part B. Wow, this part A is really long, yeah. So part B, let's move on. Oh no. Explain in terms of particles why gases can be compressed but liquids cannot. So you have to explain the reason why gases can be compressed. As you guys do know, right? This is a disaster of a drawing. My bad. as you guys do know, right, for a gas, okay, and a liquid, right? Gases, if you notice, their molecules have a lot of space between the molecules. As for a liquid, right, all the liquids molecules are compressed together already, so there doesn't seem to be any space left for the molecules to be compressed anymore. So basically, the gases, there's a lot of empty space. Let's write that down. So gas particles, okay, have much larger distance, okay, okay, between them, okay, and this, allowing the gas to be compressed. So on the other hand, liquid particles are already touching each other, so there's much less space and they cannot be compressed. Okay, that is it. Okay. So just to take note, yeah, gases, as you can see in the diagram here, a lot more space between the particles, while the liquid, as you can see here, all the particles are already touching each other already, so they cannot be compressed. Okay. Also, do remember explain in terms of particles why gases can compress, liquids cannot. Actually, you know what? I need to write the why liquids cannot be. So let me just mention or finish this. Okay. All right. So yes, good. All right. Let's move on to the next part of the question. But before that, right, is everybody clear with the answers for these questions so far? Is everybody clear so far? Chat is okay? Yeah? All right. I think we should be fine. Now we are 4 questions down. We have 6 more to go. Let's move on. All right. Okay. Right. More essays to write. Now, question 5A. There is a large puddle of water on the road, and the water in the puddle evaporates. Yeah, so as you can see here, big puddle of water evaporates. So we need to describe how evaporation in the puddle occurs, and we have to use ideas about particles in our answer. All right, so evaporation pretty much happens when the most energetic particles, right, escape from the liquid. Okay, the most energetic particles of the liquid escape the liquid, right? So and so basically that happens. That is how liquid particles they evaporate and turn into a gas, right? So let's write it down. Hmm. So evaporation occurs when the most Particles with the greatest kinetic energy, right? Rises, yeah, okay, in the puddle, in the puddle, rise to the surface and escapes. Once again. Yep. So basically, that's that. Right. So just to take note, evaporation occurs when the most energetic particles and with the greatest kinetic energy, right, they rise to the surface and escape from the liquid. This is how evaporation occurs. Do take note, it's a 2-mark question, so you must have two solid points to take note. The first one is most energetic particles with the greatest kinetic energy. That's the first point. Second point is it will have to rise to the surface and escape. Okay, 2 marks, 2 points, 2 valid points. Okay, all good? Yeah. All right, let's move on to 5A part 2. So, state and explain one change in the weather that can cause a faster rate of evaporation. There are actually more than one way to make evaporation go faster, right? So the first method, of course, when you have, if the weather is hotter, if the conditions are warmer, right, evaporation increases. The rate of evaporation will increase. That's the first. And the second way is if there's a wind blowing on the puddle, the evaporated water, the particles will be blown away and it will be the air above the puddle is so-called empty again for more particles to escape. So let's do the first one, shall we? So the first change is a higher temperature. Okay, sometimes direct sunlight can also be it can also be a valid reason here as well. So let's write this down. Higher temperature. Okay, means more particles gain energy and more particles get the puddle. Okay, okay. All right. The other option is windy. Is if it's windy. Okay. Yeah. Right. Let's move on. Okay. Now part B. The car travels on the dry road and the driver presses on the brakes. The car travels a distance before it comes to a rest, and this distance is called the braking distance. So we are to state and explain how the braking distance changes when the road is wet. Wow, this is a complete 180 different topic from what we have learned, what we have answered above. Interesting. Okay, so basically on a dry road, right, there's better friction between a car, right, and the road. So in a dry road, the friction is stronger. But on a wet road, the friction is lower, right? So because of that, right, when the road is wet, the braking distance should be longer. Let's write down. Here. Pardon the horrendous handwriting here. Let me just do this properly again. Now we need to explain. This is because the friction between the tires and the road has decreased. So yeah, quite a lot to write just for 1 mark, yeah? So you have to state and explain. So the statement is, on the wet road, the distance is longer. The explanation is, this is because the friction between the tires and the road has decreased. All right, so we need to state and explain to get this 1 mark. All right, okay. All right, let's move on. Fantastic. I'm seeing somebody wanting to share this with your friends. That's great. All right, so let's move on with part 6A. Okay, now this is a little bit fun to do. We got some drawing we need to do now. Okay, so as you can see here, figure 6.1 shows a successive crest of water approaching a boundary, and region B, the speed of the waves in region B is lower than the speed of waves in region A. So we are supposed to draw the crest in region B. So when the speed, right, of the wave, right, is lower, okay, let's write the lower speed. Okay, right. So we also do know over here the wave is traveling in this direct. Oh my goodness, I'm so sorry about that. Yeah. Okay. So this should be the case. Yeah, this should be here. So the wave should travel something like this direction. So oh my goodness, this was horrible. Yeah, there. Okay. Uh, that doesn't look right either. All right, never mind about that. So basically, the waves travel this direction and it goes into this boundary where it moves in lower speed. When it moves in lower speed, right, the most important thing we need to note is the wavelength becomes shorter and the direction of the wave. Oops, my goodness. Okay, oops, that's my bad. Right, and then the waves should bend. So it goes this way originally. It should bend down this way in terms of its direction. So our resultant wave that we've drawn should look something a bit like this. Okay. Oops. This. Okay. I know my drawing skills aren't the best, but as you can see, let me just erase this bit, erase that bit, erase this bit. All right. As you can see, when your waves come in here, it kind of bends and it now moves about slightly bent direction in this direction now. All right. So this wave is undergoing refraction. So first thing first, as you can see here, we have the speed of the waves is, we note the speed is lower. So we have to draw the crest and crest the waves like this. So the first mark is given that, right, the the lines are parallel to each other. Second mark is that the wavelengths, the length between the waves is actually shorter compared to here. And number three, it all moves this direction. The thing is angled in this direction. Okay, so this is done. 3 marks done. And as we stated, right, this is a phenomenon called refraction. So just write it down too. Okay, so this is the phenomenon of refraction of the wave, right? And that backs you 4 marks. Easy peasy. Okay, 4 marks, done. Right. So far, so good, huh? Okay, now let's move on to question 6 already. Wow, my goodness. Question 6, part B. As you can see here, light can be totally internally reflected when striking the boundary between two different regions. State two conditions that are necessary for total internal reflection to occur. So, as you know, I need to draw this somewhere. My goodness, I have space. All right. So this is the boundary layer. This is the normal. Okay. So for total internal reflection to occur, right? Your light, right? This is the okay. So it's optically denser, and this is the optically less dense. Okay. The light must come out from a denser to a less dense region. That's the first option. Okay, right? The speed, or should I say, the speed of light here should be lower than the speed of light here. All right. Then next thing to note is, right, the angle of incidence must be greater. Okay, the angle of incidence, right? It should be greater than something called the critical angle. The critical angle occurs when your light comes in here and it refracts just nice. Oh my goodness, that's bad. That's bad. Remove. Your critical angle is when your light enters in this direction, it actually continues this direction. This is called the critical angle. Okay, so we have our two conditions right now. First, the angle of incidence should be greater than the angle or than the critical angle. My goodness. Okay, go away. Okay. So total internal reaction occurs like this. When this angle is bigger than your critical angle, it will undergo total internal reflection. Okay, this is okay. Next, but next thing you do is, right, the light must be in an optically denser medium compared to the other one, right? So that's, and because of that, right, the speed of light in the denser medium is lower than the light in the optically, less dense medium. So let's write that. The speed of light, right, in the first region must be lower than the speed of light in the second region. The first region is the second region. Okay. All right. Now let's move on to B part 2. We are to state two advantages of using optical fibers for transmitting high-speed broadband. I'm pretty sure everybody here uses broadband already, right? Back then, in my time, we used dial-up connection and that thing is slow, like what, 5 kilobytes a second? That's unbearable, right? So those of you guys who have experienced what we have experienced before, I think you won't be you're all unks at this rate. All right, let's move on. So the two advantages of using optical fibers are basically, number one, right? Number one, it has greater bandwidth, right? And it also it will not be affected by what the heck happened. I'm so sorry. All right, so let's just before I write down anything, let's just list down the advantages of optical fibers. So number one, it does have greater bandwidth for faster transmission, and number two, it has little data or signal losses. All right, because it basically is made of light, and light cannot be interfered much by other means, right? There are more other answers. For example, it's able to carry large amounts of data and information, is more secure, and basically that's it. So let's write down the two reasons. Okay. Oh, okay. It allows for greater bandwidth for high rate of data transmission. Number two, it has little data or signal loss. All right. Hmm. That's great. So with that, question 6 is done. I will now let my uh colleague Mr. Narayan to take out more answers as we wait for a short while. There we go. All right, welcome back, everybody. So let's continue with the next part of the question. The next question. All right. So let's continue with question 7A. All right. So the circuit here, as you said here, as they said here, the circuit consists of an AC supply with two lamps, and the lamps are connected in parallel. So we are to draw the circuit diagram, right? Okay, so a circuit is has an AC supply. As you do know, an AC supply looks something like this, and then you have to do the squiggly line here and write AC, all right? And then we need to connect this to two lamps. So let's just draw this thing properly, like this, like this, like this. Right. So okay, just make sure the wires are connected properly. Yeah, this is a negative example. You have to draw a nice straight line. Oh, all right. So first, let's connect these together. All right. So the circuit symbol for a lamp is a circle and a cross inside, like this. Make sure all your circuit components are well connected together. Right, like this, like this. Okay. Okay. So first, you must make sure you must have the AC, which gives you 1 mark. And number two, the second mark is everything is connected to two lamps like this, which is parallel. They must be connected in parallel. Okay. This is a parallel circuit. Okay. Now let's move on with this. Part B. The EMF of an AC supply is 230 volts. We connected this to this supply. The resistance of the one lamp is 1200 ohms, and the resistance of the other lamp is 800 ohms. So we have to calculate the current in the 800 ohm lamp. So basically, we know that in here the lamps are connected in parallel. right? So since they are connected in parallel, both lamps have the same potential difference. So what we can do over here is this. So let's just take a look first. Okay, both lamps have the same PD. So let's calculate the current of the 800 ohm lamp. So I, which is the current, is equals to the potential difference divided by the resistance of the lamp. So we have 230 volts divided by the resistance, which is 800, which is equals to 10. This, you do the calculations, you get 0.2875 ohms. And as per usual, let's do the conversion for two significant figures. We round this up. Excuse me. Round this to 0.29, which is two significant figures. And this is, oh my goodness, forgot the units. Sorry about that. The current is 0.29 amperes. And this has to be in two significant figures, like that. All right, let's write it down here. 0.29 amperes. Here we go. So this is our first. As you can see here, there are 2 marks, right? So writing down I equals to V over R will gain you 1 mark, and calculating the correct answer over here gains you the 2nd mark. Okay? Okay? Good. That looking clear. Good. Fantastic. Let's move on. All right. Now, let's calculate the energy used by the 800 ohm lamp in 5 hours. And we have to give our answer in kilowatt hours. All right. So, first things first, we need to find what is the power output of this lamp. Okay. So, power is equals to voltage times the current, which we already found just now, 0.29, right? So, let's do this. 230 multiplied by 0.29, which you get 0.0667 kilowatt, right? Okay. Now we found the power output of one lamp. Okay, because this is oh my goodness, I should have done this better. You actually get 66.7 watts, but we need to convert it into kilowatts because we have to convert everything into kilowatt hours. So 66.7 watts is equals to 0.0667 kilowatts. All right. For now, we don't need to do any conversions to specific here. We still need to continue with the calculations. Right. So energy. Now we can find the energy used in 5 hours. Okay. Okay. So energy used is equal to power multiplied by time. Okay. And this is equals to 0.0667 multiplied by 5 hours, okay, which is equals to 0.3335. We will do the conversion to 0.33 kilowatt hours, right? So to take note, because our energy is to be done in kilowatt hours, so the power here must be in kilowatts, and the time here must be in hours, so we can get the proper units later. Okay? And the answer is 0.33 kilowatt hour. And of course, this is in two significant figures. Okay. As for the mark allocation, this is a 3-mark question. First thing, writing down what gets you power over here and writing it in kilowatts gets you 1 mark here. So Writing down energy is equal to power multiplied by time gets you another mark. And getting the correct answer over here, the correct number over here, gets you the third and final mark for this question. Easy, isn't it? Right? So let's move on to 7 part 3 over here. Again. Okay. All right. Let's move on. 7. Question 7. Is it 7, right? Yeah, question 7b, part 3. We are now to calculate the combined resistance of the two lamps in this circuit. Right? So we already been given the resistance of lamp number 1 is equals to 1200 ohms. And then the resistance of lamp number 2 is equals to 800 ohms. Okay? So let's bring out the equation for the combined resistance of parallel circuits. As you remember, 1 over R total is equals to 1 over R1 plus 1 over R2. Okay, this is for parallel circuits, yeah? Remember that? So let's just continue with that. 1 over R1 is 1200 plus 1 over 800. Okay? Now let's do this. Let's flip this thing over. So we basically multiply this over to this side. Okay? And then we multiply this over to that side. So we do this. No, multiply, sorry, we divide this over to this side. So we get R total be equals to 1 over 1200 plus 1 over 800. Now let's do the mathematics. You get 48010, which is 480 ohms in two significant figures. Okay, so the total resistance here is 480 ohms. All right, so this is a 2-mark question. So firstly, as long as you write down this equation over here, this gives you 1 mark awarded, and getting the correct answer here gets you a 2nd mark. Right? 480. Fantastic. Good job. Anshika, good job. Move on. Before we move on, right, any other questions for question number 7? Chat, please go ahead and ask any questions to our very helpful and very kind tutor, Mr. Narayan. So if you have any questions, please feel free to ask. Okay, we have 15 questions, so do let us know. Okay. Right, let's move on to question 8. This is a funky looking setup. All right, so before I look at this very interesting looking setup right here, let's do question 8a. So question 8a wants you to state what is meant by a magnetic field. So as you guys know, a magnetic field is essentially a region where, right, a magnetic pole can experience a force. So for instance, you have a magnet here, north and south. This is a magnetic field, right? Do you guys remember this? This is north goes out, south goes in. And when you put another magnet over here, let's say another south pole, it gets attracted. So let's write down the actual definition of a magnetic field, right? A magnetic field is a region, right, where a magnetic pole, it doesn't matter north or south, experiences a force. And writing that gives you 1 mark. Okay, so for those of you guys who are a little bit more, finding all this difficult to memorize, I think, sometimes you have to memorize a few definitions, and this will really help you to get these extra 1 marks, 2 marks in the exam. Okay, right. Definition done. Let's move on to this very, very strange looking uh, diagram over here. Okay, so over here in figure 8.1, we have an emitter connected to a coil. This is the emitter connected to a coil over here. And this coil is wound over a thin plastic cylinder. And here, a trolley is placed on a curved track which passes through the cylinder like this. Okay. The trolley is then released from this point, right? This point here, shown here, and it travels through the coil from the right to the left. And then it stops somewhere around here. Okay? And then it will travel back from left to the right. So, as stated in the question, when it does this left to the right motion, it would have lower maximum speed compared to when it moves from the right to the left. Okay? This plastic cylinder does not affect the magnetic field, and a magnet is fixed to the trolley. As you can see here, this is a magnet. Okay? Alright, so first things first, we need to state, right, why there is a lower maximum speed when a trolley travels back from left to right. Okay? So we need to state the reason, right? So as you can see here, this is the topic of magnetic induction, right? So when the trolley moves from here into the coil over here, right? The magnet here will induce this coil, right? It induces a magnetic field on this coil that resists this motion. So it will slow down this trolley speed, okay, as it moves through the coil. So let's just write that down first. So when it moves from here through here, right, and back up here, right, it loses some speed here, loses some kinetic energy here. So when it moves back up here, it has less kinetic energy, and it converts this less kinetic energy into gravitational potential energy. And thus, there is less energy on the left side when it moves from left to right compared to right to left. Okay? That's because the induced magnetic field here slows down the trolley. So let's write this down in a much more structured way than be rambling about physics. Right? Let's go on. Okay. As a magnet. Okay. So let me just write this down a little bit nicer. Okay. The magnet on the trolley induces a magnetic field okay in the coil that opposes the magnetic field of the trolley. Okay, this slows down the trolley. Okay, this I need to write this thing down here. Slows it down. Okay. Okay. All clear? All right, let's move on. Now, the next part of the question, part B2, it shows a close-up of the emitter that is placed up here, right? So as the trolley enters the coil, moving from right to left, the ammeter deflects to the left and then returns back to 0. Okay? And then we are to state and explain any changes to the deflection of the ammeter as the trolley, right, enters the coil and moves from left to right. So basically, we want to know what happens to the ammeter when the trolley moves in this direction. Okay. So, first thing what we do know is, right, that when the trolley moves from right to left, the ammeter deflects leftwards. Okay? And when the trolley moves from left to right, the ammeter should also continue to deflect left, and there's no change in the motion. But there is a change in the amount of deflection. This is because as the trolley moves from left to right, when the trolley moves from left to right, it has lower speed. So which means the current induced in here is lower compared to when it moves from right to left. Okay? Right. So basically, when it moves from left to right, the induced current over here is still exerting in the same the induces a current that moves in the same direction as when the trolley moves from right to left, but the deflection will be less. So let's write that down. Okay, so as the trolley, okay, moves from left to right, okay, it causes a deflection to the left. Okay, that is less than the first deflection. Sorry. That's the first deflection. Okay. This is the first one. This is the first mark you get. So you have to first state what happens. So the statement is that the trolley moves from the trolley will cause a deflection to the left that is less than the first deflection. Okay. We need to explain what happened. So first thing first, we need to explain why the induced current, the deflection is still the same direction. This is because the induced current still flows in the same direction. Okay, that's the first part done. And now we need to explain why it deflects less than the first one. Okay. However, since the trolley moves slower, smaller induced EMF in the coil would deflect the mirror, would deflect the needle. Sorry, excuse me. All right. So far, so good. Okay. So basically, this 3-mark question can be split into 3 parts, of course. We first need to state what will happen to the deflection of the end meter. Okay. So the first part is it will cause a deflection to the left. Basically, the direction is the left is the same, but the amount it deflects is less than the first deflection. This is the first mark. The second mark is to explain why why it still deflects to the left. This is because the induced current still flows in the same direction, and thus it still deflects towards the left. Now that's the second mark. The third mark will need to explain why is it moving. Why is the deflection less? As we see, the trolley moves slower, and there's a smaller induced EMF in the coil. This would mean it would deflect a little less. And that gives you the full 3 marks required for this long essay. Okay? Everybody clear? Right. That's fantastic. And with that done, let's move on to question number 9. All right, we are almost done already. 2 more questions to go. Okay, so question 9, we are shown a beam of radiation in vacuum, and this beam contains alpha, beta, and gamma radiation. So alpha particles, beta particles, and gamma radiation. So this beam enters a region where there's a strong uniform magnetic field and the direction is into the page. Okay? So this is where your Fleming's left-hand rule will come in very handy. So first things first, we can draw the easiest one for now. As you can see, they want you to draw and label the paths for the alpha particles, the beta particles, and the gamma radiation. So for this, the easiest so far is to do the gamma radiation because it will not be affected by anything. It still continues in a straight line. So we can just draw one straight line like this, and we just draw it this way. Oops, my bad. Okay, our gamma radiation should go straight all the way without any changes, and we should label this gamma. Okay, so this one is done. Now, for the alpha particles, right, we need to use the Fleming's left-hand rule. So as you do see, there is a region of uniform magnetic field into the page. So as you can remember, this is the force exerted, this is the magnetic field, and this is the current. So as you can see, the current moves in the same direction as the beam of radiation. And then of course, your magnetic field is a X down there, so it points into the screen. So this means, I think you can look at it better in this direction. I think this direction. Or is it or is it in this direction? Yes, I think it's much better this direction. As you can see, my middle finger is pointing to the to you guys. I think it's pointing to the left, but it's supposed to be pointing to this direction, right? The index finger points into the screen, your middle finger points to your right, and so the exerted force should point upwards. Okay, so which means, because this is alpha particles, right? Alpha particles, when they move in this direction, the current moves to the right, like this. Okay, and using Fleming's left-hand rule, we can deduce that the path of the alpha particle should move something like this. It should have a force exerting upwards. Yes. Okay, so alpha particles go upwards. Yes. And also, thank you for the reminder, Narayan sir. For a positive charge like alpha particles, right? Alpha particle is a positive charge. The direction of current and the direction of the beam should be the same. Okay, so alpha particles move upwards like this. All right, that's clear. Now, here's the slightly trickier one, which is the beta particles. As beta particles are negative and negatively charged, they are electrons after all. So for negative charge, right, the direction of the travel of the particle and the current is reversed. So if the beta particle moves to the right, the current moves to the left. So once again, let's take out our handy Fleming's left hand rule and let's do the direction check, right? Actually, if you know what, it should be the direction of the force should be different, but let's show you how it's done. So once again, your index finger points into the screen. However, your middle finger, which is the current, it should be pointing towards your left. Okay, now you can see, right? The force exerted on the beta particle exerts it downwards. So our beta particles should be pushed downwards. But here's one more thing. The alpha particle is a helium nuclei, which is basically a charge of +2 is made up of 2 protons and 2 neutrons. Okay, this thing is quite heavy. A beta particle is made up of an electron, which has a very negligible mass. So basically, it uses this field will exert the same amount of force on the alpha particle as the beta particle, and because of that, it pushes the beta particle much more compared to the alpha particle. As a result, a beta particle should bend a lot more compared to your alpha particle, and this will get you your 4 marks in total. Easy peasy, yeah. All right, all good. Okay, fantastic. So just remember, for the alpha, also another trick to know is for this kind of questions, right? The gamma radiation will not be affected by any electric field nor any magnetic field. The alpha particle will go in one direction, while the beta particle will always go in the opposite direction. And most importantly, the alpha particle will be affected not as much compared to the beta particle because the alpha particle is a lot heavier and a lot more massive compared to the beta particle. And as for force of inertia, you push it less the amount of force it uses is the same. So the alpha particle is pushed less compared to the beta particle. All right, let's move on. Okay, so now let's go on to part B. Okay, part B is now looking at 5 radioactive sources. Okay. But first, before we even look at any of this, we want to know what exactly is the half-life of a radioactive isotope. We need to define the half-life of a radioactive isotope. So simply put, I think you can just write this down. All right, the half-life is simply of the isotope is simply the time taken for the half of the number of radioactive nuclei to decay. All right, so let's write it down. All right, so this is pretty straightforward, yeah? Okay, now let's move on. So now let's move on to B part 2. So over here, as you can see, figure 9.2 shows a simplified diagram of a machine that produces thin sheets of aluminium of constant thickness. Okay. And right over here, you can see this radiation detector that is used to measure the aluminum sheets and control the gap between the rollers. So we are supposed to go to table 9.1 to select the most suitable radioactive source right over here if for to be used as for it to be used over here. Okay, so let's go through each of these one by one. So as you can see here, right, an aluminum sheet is this radiation detector needs to detect some radiation going through this. So if the sheet is too thick, right, the radiation is bounce off, and the radiation bounce off, and then the rollers will make the sheet thinner. And if the radiation detector detects too much radiation, the rollers will open a bit wider to make the sheet thicker. So for this question, it's pretty much very straightforward that you want to use beta radiation, because alpha radiation, as you can see here, right? Alpha radiation can be blocked by a thin sheet of paper, much less an aluminium sheet. So this pretty much eliminates all the alpha radiation. Okay. As for gamma radiation it passes through everything. It needs a very thick layer of lead to be stopped. So this means gamma radiation is also out of the question. Now we are left with the two beta emissions, right? One has a half-life of 29 years, the other has a half-life of 14 days. So if we were to use the one with 14 days, right, we will need to change the source every 14 days after a very short time, because as you can see, every 14 days the number of radioactive isotopes in that sample has halved. So maybe over 30 days, over 14 times, doing every 14 days, right? It keeps getting less and less and less. So this source S kind of works, but you need to keep changing the source every now and then. So this is not as effective compared to source R, which has a half-life of 29 years. This means the source can be used for a much longer period of time. So that's why you want to use source R. And most suitable source over here is R. Okay? Now let's determine why this is possible. Number one, R has a long half-life. Okay? Which means it doesn't need to be replaced. After long, it doesn't need to be replaced for a long time. Okay. Also, now this is the first mark we want to add. The second mark we want to say is the thin aluminium sheet, okay, would absorb all alpha radiation and gamma radiation be blocked. Alright? So only beta radiation would vary the count rate, okay, depending on the signal. for this application. So pretty much, right, this is a 4-mark question. So the first mark is we find the most suitable source, right, which is R. And now the 3 marks is we need to explain why R is the best for this, and we also need to explain why the other sources are not not suitable for it. So basically, the first mark is if the aluminum sheet, basically for alpha radiation, the aluminum sheet would absorb all of it, right? And gamma radiation cannot be blocked by the aluminum sheet. That's why all alpha and gamma sources are removed. And now we also need to explain why beta is the most suitable, because beta radiation, only beta radiation would vary the count rate, right? And this depends on the thickness of the aluminum sheet. And as for either between source R or source S, as explained before, source S has a very short half-life of 14 days compared to source R of 29 years. So which means the long half-life of R means the source does not have to be replaced for a long time. Okay, so writing these 3 points down will get you your 3 marks here, and the most suitable source here, given correctly, give you your 4th mark. So this will make short work of all 4 marks for this question. Okay, all good? Once that's done, let's move on to our last question, question 10. Right. Okay, now a bit more calculations we need to do here. Okay, and let's continue. Okay, so this is the easy one. Fill in the gaps in the description of how an accretion model explains the formation of the solar system. So we need to describe the accretion model, all right? So basically, in this model, right, the planets that are closest to the sun are small and rocky, while the planets further away from the sun are large and gaseous. Okay? And all the planets are formed when a cloud of gas and dust collapse due to gravitational force. And last but not least, the rotation of material in the cloud forms an accretion disk. And just like that, 4 marks in the bag. Easiest 4 marks, isn't it? Okay. So yeah, the planets nearer to the sun, according to our solar system, Mercury, Venus, Earth, and Mars, they are rocky planets. Planets furthest from the sun are gaseous, such as Jupiter, Saturn, Neptune, and Uranus. And all these planets are formed when the cloud of gas collapses due to gravitational force, and the rotation of the material of the cloud forms an accretion disk. All right, pretty easy. That is 4 marks in the bag. And let's move on to part B. So the time taken for light to travel from the moon to Earth is 1.3 seconds. Now we need to calculate the distance of the moon from the Earth and give it in meters. All right, so first things first, we know what's the speed of light, right? Speed of light is equals to 3.0 times 10 to the power of 8 meters per second. Right. So the light takes 1.3 seconds to travel between the moon and Earth. So distance is equals distance is equals to speed times time, equals to 3.0 times 10 to the power of 8, which is the speed of light, multiplied by 1.3 seconds. Okay? And with that, we can just do the calculations. 3 times 1.3 equals to 3.9 times 10 to the power of 8 meters, right? Equals 3 times 1.3 equals to 3.9. So easy peasy. So that's right, it's here. So for this, right, we are given 1 mark if we give the speed of light. We given 1 mark if we write this correct equation. Distance is equal to speed times time, and 1 mark if we write the correct answer, if we calculate the correct answer. Okay. Now let's move on to the last part of this question, which is also the last part of this entire paper. All right, so first things first, we now know the Whirlpool galaxy is 2.3 times 10 to the power of 7 light years away from Earth. And the current value of the Hubble constant is 2.2 times 10 to the power minus 18 per second. Okay, so we need to calculate at the speed which the Whirlpool galaxy is moving away from the Earth. So I don't want to draw a diagram here, but let's just do this, all right? So firstly, we need to calculate how many meters is 1 light year. So 1 light year is equals to 9.5 times 10 to the power of 5, 10 to the power of 15, I'm sorry, meters, okay? So this is 1 light year. The Whirlpool galaxy is 2.3 times 10 to the power of 17, so 10 to the power of 7, I bet. So 2.3 times 10 to the power of 7 light years, right, is equals to 9.5 times 10 to the power of 15 multiplied by this big number here, 2.3 times 10 to the power of 7. Now we do the maths. Okay, 2.185, right, times 10 to the power of 23 meters. Okay, now we have the distance of the Messier 51, the Whirlpool galaxy, in meters. Okay, fantastic. Now we also are given the Hubble constant, which is 2.2 times 10 to the power of 10 to the power of minus 18 per second. So let's write down this equation here. This equation over here, v, this is the distance of the velocity where the object is moving away, is equals to Hubble constant, which is h naught, multiplied by distance away, which is this d. Okay, this is equals to 2.2 times 10 to the power minus 18 multiplied by 2.185 times 10 to the power of 23. Okay, this would get you 4.807 times 10 to the power 5 meters per second. As you can know, this is in seconds. This is per second. This is in meters. So when you multiply these together, you get meters per second. You get speed, right? So this is equals. That's not equals. I'm sorry. Now we need to do the two significant thing. Now we round it down to 4.8 times 10 to the power of 5 meters per second, which is in two significant figures. 4.8 times 10 to the power of 5 meters per second. Okay? Right. So that is the answer. And as for the number of marks awarded here, we have 3 marks awarded here. So as long as you're able to list down, right, what is the number of the number of meters in 1 light year, that gets you 1 mark. Write down this equation, it gets you a 2nd mark. And writing down the correct answer, calculating the correct answer gets you the 3rd mark. Okay, and that gets you the full 3 marks. And with that done, we are done with the paper. Thank you for sticking through this. And yeah, there we are done. We are done with today's paper. Right, fantastic. Okay, so now that we are done with today's paper, I want to thank everybody who sat through with us to listen through this really long and very nice explanation. Now, please go ahead and ask any questions in our comment section, and please write down anything in chat, and my teachers and I will look through your questions and answer them accordingly. Thank you so much.